Hi, Kenzie.
All right, whoever's watching this video, Kenzie, McLean, whoever's watching this, here you go. We are on section 5.2. This is example 4 is where we're starting. At the top of this page, because it is a new page, the thing that I want you to write down is NCX. P to the X, Q to the N minus X. That thing you need to write down at the top of the page because we are going to use him. Okay? All right.
No, I know.
Yeah.
Example 4, devil of a problem. We're going to write down some information. The 4 things that we need to collect are what N is, what X is, what P is, and what Q is. Okay? Based on a Harris poll, 60% of adults believe in the devil. I think that's interesting. 60%. Do you think that's accurate?
I've met Holly, so I don't know.
60% believe in the devil. What is 60%? Where does 60% go?
Only when she dressed up as it.
Where does 60% go?
It is your Q.
It is your P. Okay? Remember what yesterday when I said that P was the probability of success? So evidently success means you believe in the devil. So it doesn't necessarily, don't get hung up on the whole success failure thing. Okay, P is 0.6, Q is 0.4. I wish they would have, instead of putting success versus failure, I wish they would have put like what you're interested in and what you're not interested in, right? Like you're interested in people who are believe in the devil. You're not interested in people who don't believe in the devil. So 0.4. Anyway, so success versus failure doesn't necessarily mean success versus failure. Assuming that we randomly select 5 adults, what is that? N, we're choosing 5. A tells me what X is, the probability that exactly 3 of the 5 adults believe in the devil.
No way.
So X is 3, and I'm going to do A over here, and then I'm going to split and do B, okay? A is exactly 3 out of 5, so I'm just going to do 5, C3, okay? P is 0.6, and I do that to the what power?
No.
The third power, and 0.4 is to the second power. Those two exponents should add up to be your total number, okay? I want 3 people who believe in the devil, 2 people who don't believe in the devil. That's a total of 5, okay? So, do that in your calculator. Practice typing that in. Let's see what we get.
Just like.
Yeah, but he was like,
Insane.
rapid fire rap.
It's 0.345.
He was like,
Times
How do you know that? You're blowing your nose.
6
Said it the
to the
wrong.
that's
third
what, no, it's
times
like
0.4 to the
I
second.
believe it.
Point?
3,
Oh, they
4,
walked
5.
one time.
0.3456.
4 points, you should do all 4.
Okay, now, because they're going to ask us these questions, what does that mean?
It means 34.56% of Americans in
Nope.
a group of 5
Nope.
believe in the devil.
No. It means I have a 34.56% chance of exactly 3 out of 5 people believe in the devil. Does that make sense? There is a 35-ish% chance that if I have 5 people, exactly 3 of them believe in the devil and 2 of them do not. Okay? Make sense? All right, part B. This is where it gets a little bit more messy. The probability that the number of adults who believe in the devil is at least 2. Okay? So let's talk about the combinations that we could get.
Throw 1 through, then go
So
1
these
by.
are believe, these are not believe, right? We're selecting 5 people. So I could have 0 believe and all 5 of them not believe. I could have 1 and 4, 2 and 3, 3 and 2, 4 and 1, and 5 and 0. Those are the combinations that I could have, okay? We want at least 2 of them believe, all right? So let's select those things here. Is the first combination at least 2 believing? No. Second combination, at least 2 believing. Third combination, at least 2 believing. Yes. Fourth combination, at least 2 believing. Yes. Next one, at least 2. Yes. Next one, at least 2. Okay, now, when I write this up here, we have 6 total combinations, and we want 4 of them, which means I'm going to have to do this thing 4 times.
Not happening.
Except, what would be easier?
There's more? Do the first 2 and subtract.
Do the first 2, since there's only 2 of them I have to do, and then subtract it from 100%, right? I don't want that. These 2 combinations is not at least 2. Not at least 2. But it's faster if I do those two and then subtract it from 100%. Correct? Right? Okay? So let's do those two. Okay, so I want the combinations of 0 believe and 5 not believe, okay? So the way that this is set up, the way that this equation is set up, we're only going off of the believe part, right? So the not believe column is kind of gone. We're only going off of the not believe column. So the first one would be 5C what? 5C 0, 0.6 to the 0, 0.4 to the 5. Okay, the next one, if we set this up, this would be 5C 1, 0.6 to the 1, 0.4 to the 4. Okay, let's figure out what each one of those is. And then we're going to end up adding them together and then subtracting from 100%. Okay? Anybody have these numbers?
It's 0.01024 and
0.01024?
Yep.
0.0102? We're going to go 4 decimal places.
Okay, and now
Okay.
for the 0, 1, and then the 1, 1 is 0.0768.
0768?
Yep.
Okay?
Is that
Woo!
102?
Yep, 0.0102. 68. There's an 8 right there. If I add those two together, that is 0. Oh boy.
I just give you the answer.
0.870. Yeah?
I don't know. I just subtract.
So 8%, basically, almost 9%, okay? So if I subtract that from 100%, or since it's a decimal, I'm subtracting it from 1, so 1 minus that would give me 0.9130, yeah? So there is a 91.3% chance that what? 91.3% chance that at least two out of 5 believe in the devil. Okay, does that make sense? If I have a room full of 5 people, I have a 91% chance that at least 2 of them believe in the devil. Now that's a pretty high probability, okay? Because 60% is a pretty high chance of believing in the first place, right? At least 2. Any one of them has a 60% chance of believing, so at least 2 out of 5, there's a pretty high chance that I'm going to get at least 2 out of 5.
Hey, if they
Right.
tell us to use a probability table, we just punch into our calculator instead.
What?
If they tell us to use a probability table on the homework, you just punch it in your calculator instead.
What do you mean? You just add the numbers up?
They say use a binomial probability table. Like, can I just do like what we're doing now?
Which one are you talking about?
Number 4.
Number 4?
Yeah.
Use a binomial probability table to find the probability that the number... Okay, just wait a second. I'm going to get to that. Just wait a second.
I'll go to 5 then.
Just wait. Okay? Because I'm going to give you a table with a cheat sheet. Okay? All right, the last one, part 2, says using mean and standard deviation. Okay? So when we did a mean and standard deviation of a probability distribution table like this guy, we would multiply them by each other to find the mean, and then we would add those up together. Do you remember doing that? Okay? Now, if they don't give you the table, here is what you can do. To find the mean, the average, you just take the number of trials that you have times the probability that you want. Okay? So this is the probability of success, they call it. Probability of success. And this will give you the number on average. Success. This will give you the number on average that it will be. So, example down here. The chapter problem and example 3 involved 460 overtime NFL football games. The probability of getting a heads on a coin toss is 0.5, and the probability of getting a tails on a coin toss is 0.5 again. Okay? So, what should happen? Approximately how many teams should win? How many teams should lose? If I'm doing 460.
50, so
Since it's 50-50, 50-50 of 460 would split it into 230 and 230. That is the average. We compute the average because mu is equal to n times p, which is equal to 460 times p was 0.5. I'm just taking half of 460, which is 230. You guys do that in your head automatically, but this is the equation for it. You take the number of trials times the probability that it's going to happen. Okay, you guys already kind of had that figured out ahead of time. So 230. The mean number of wins is 230 out of 460. Okay? Use the range rule of thumb to find the values separating the number of wins that are significantly low, significantly high. So we need to know the standard deviation first before we can do that stuff. Okay, so standard deviation, and the way of finding standard deviation is the square root. It's right here. The square root of NPQ is standard deviation. Square root of N times P times Q. Okay, so let's compute that for the information that we're given. What is N?
460.
460. P is, whoop,
0.5.
let me erase that. 460. P is 0.5.
Yep.
Q is
0.5.
also 0.5. So multiply those together and take the square root, and that will be our standard deviation. Square root, 460 times 0.5 times 0.5.
10.7.
Let's go 2 decimal places. 10.72. I don't know what they're going to make you get. Well, I guess we're doing this pencil paper. So, yeah, as long as you're close on rounding, I'm not going to tell you which decimal to round to like the computer does online. Okay, 10.72. All right, now I want to know significantly low versus significantly high. 460 goes in the, no, wrong. 460 doesn't go in the middle there. What goes in the middle?
230.
230. The average goes in the middle, right? How do I figure out what's significantly low versus significantly high? You add 2 and subtract 2, right? Okay, so significantly low is this cutoff, significantly high is this cutoff. So I'm adding 10.72 twice. And I'm subtracting 10.72 twice. Okay, so something like, I don't know, 251.44. If I subtract it,
208.56.
208.56. Okay, so if I had less than 208 teams winning, that would be a significantly low number and something is happening. Okay, if I have a higher than 251 people winning, then something is happening as well. Okay, so is the result of 252 overtime wins a significantly high number of wins? Yes, it is. So what can we conclude from that? They don't ask us this, but what do we conclude from that?
Something's rigged.
The coin toss is probably rigging it, right? The coin toss is making it so that the person who is winning the coin toss has a more favorable outcome, right? Okay, so yes, 252 is significantly high number of wins. Okay. All right, good? Yes, yes? All right, you should have done 1 and 2. Let's do 3 together on your homework sheet. We'll do this one together, and then you'll kind of have a starting point, okay? And then make sure I go over number 4. All right, multiple choice questions. Each have 5 possible answers. They are A, B, C, D, and E, kind of like the ACT does. One of which is a correct answer. Assume that you guess the answers to 3 such questions. Use the multiplication rule to find the probability of a correct, a wrong, and a correct. Do you see that? Probability of CWC, that means correct, wrong, correct, okay? Where C denotes a correct answer and W denotes a wrong answer. Now, we are going off of the fact that I am randomly guessing, okay? If I actually put thought into the question, I have a higher chance of this happening, right? Or of getting the right answer.
1/5.
Okay, so probability of correct is 1/5. There is one answer out of 5 that is a correct answer. Now, what's the probability of getting the second one wrong? 4 out of 5. What do I do with those 2 fractions? You multiply them because they're individual. They're like 2 different questions, right? And then I multiply that again by another correct answer would be 1 out of 5. So 4/125?
Yep.
Yeah?
Yep.
And what's that as a decimal?
Oh, geez, you're
I'm sorry. It's like 3% maybe.
3.2%.
3.2%. Okay, so I have a 3.2% chance of that happening if I guess randomly. Okay, that's according to this. Now, if I actually put some thought into it and actually read the question, that's more likely to happen. But, this is just by random guessing the chances of that happening. Okay? Part B, beginning with a correct, wrong, correct, make a complete list of different possible arrangements of 2 correct answers and 1 wrong answer. Then find the probability for each entry in the list. Oh my gosh, what are they asking for here? Beginning with correct, wrong, correct. Make a complete list of the different possible arrangements of 2 correct answers and a wrong one. Oh, okay. Two correct answers and a wrong one. So I could have a correct, wrong, correct, or I could have a correct, correct, wrong. Does that make sense? Okay, I want 2 correct and 1 wrong. So what's another combination I could have? Wrong, correct, correct. Anything else?
No, that's it.
Is that it? Okay. That's kind of like the heads versus tails example. There was 3 out of 8, right? Because there's 8 total combinations. Find the probability for each entry in the list. Okay. So each one of these has a 1/8 chance of happening, right? 1 out of 8, 1 out of 8, 1 out of 8. Do you guys understand why it's 1/8? There are 8 total combinations, okay? If I have 3 things here, it could be one of 2 things. It could be correct, wrong, correct, or excuse me, it could be correct or wrong, correct or wrong, correct or wrong. So there are 8 possible combinations that I could have out of this list. Each one of those is 1/8. So what is the probability of getting, I don't know if I like the way that this is, then
Well, it
find
should
the
be
probability
correct.
for each entry in the list.
It should be that 3.2%.
Yes.
It don't matter what order you multiply them in, it should be the exact same probability.
Yes, correct. Yeah. So each one of these is going to have a 3.2% chance of happening. 3.2% chance of happening, 3.2% chance of happening. Okay, now, one of the other 8 combinations, I'm going to talk to you about this real quick, is a wrong, wrong, wrong. Okay, a wrong, wrong, wrong does not have a 3.2% chance of happening, right? Wrong, wrong, wrong would be 4/5 times 4/5 times 4/5, right?
Yeah.
Which would be 64/125, yeah? So that has a higher chance of occurring in this table according to that, yeah?
51.2.
51.2. So there's a 51.2% chance that I'm going to get a wrong, wrong, wrong.
Okay.
Does that make sense? So not each one of these combinations, the correct, wrong, correct, blah, 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 all of these 8 combinations are going to be weighted the same.
So,
It was only 1/8, 1/8, 1/8 if I have a 50% chance of getting it right. So 1/8, 1/8, 1/8, that would occur if correct and wrong would be for like a true and false question, because I would have a 50% chance of getting them right versus wrong. But in this case, I have an 80% chance of getting it wrong, because 4 out of 5 options are wrong. Does that make sense?
I'm assuming
So
that
P and Q,
part C is just
in this case, if I were to set up P and Q, P is actually equal to 0.2 and Q is actually equal to 0.8. Does that make sense? Because 1 out of 5 answers is correct, 4 out of 5 answers is wrong. Okay, so the table is no longer set up as 50-50. If it was a true and false question, yes, then it would be. But that's no longer the case, okay? Find the probability for each entry in the list. They're just wanting us to do that for 2 correct and 1 wrong, right?
Yeah.
Based on the preceding results, what is the probability of getting exactly 2 correct answers when 3 guesses are made?
3.2%.
Not quite.
9.6.
9.6. You would add all 3 of those up. Does that make sense? Because they're saying 2 correct, 1 wrong in any order. So all 3 of these will actually work. So I would add them together, 9.6% chance of getting exactly 2 correct, 1 wrong in any order. Does that make sense? Yeah? Yeah? Okay. One more thing that I'm going to do. I might run copies of this, actually. There is in your book, which you don't have. That's why I'm going to maybe make copies of this.
Oh,
Okay? Yeah. There is a table that allows you to kind of cheat on this a little bit, and you don't have to necessarily enter in every single thing. I gotta find it, and then I'll put it up on the overhead. Let's see, right here. Okay. Gotta put it up on the overhead so Kenzie can see what we're doing here. Dog scan.